Have you ever looked at your own hands, feeling the undeniable solidity of your fingers, and wondered if everything you are experiencing is nothing more than a brilliantly orchestrated illusion? Have you ever sat in the quiet stillness of a dark room, listening to the gentle rhythm of your own breathing, and felt a sudden, strange detachment from the physical world around you? We move through our lives with absolute certainty that the ground beneath our feet is firm, that the sky above our heads is vast, and that the universe is made of tangible, physical matter. The coffee cup on your desk feels heavy. The wood of your door feels hard against your knuckles. The gentle wind blowing against your face feels undeniably real. But the deeper we look into the fundamental nature of reality, the more that comforting solidity begins to slip away, like fine, dry sand falling endlessly through our open fingers. When scientists peer into the deepest microscopic realms, past the complex biological cells, past the elaborate molecular chains, past the tiny atoms themselves, they do not find solid building blocks waiting for them in the dark. Instead, they find a swirling, dancing mathematics. They find vast, unimaginable oceans of silent, empty space. And most surprisingly of all, they are beginning to find strange, highly organized patterns that look suspiciously like the digital code used to run computer simulations. For thousands of years, human beings have looked up at the glittering stars scattered across the night sky and wondered about the true nature of the cosmos. Ancient philosophers sat under that same celestial canopy and debated whether the world was made of earth, water, air, and fire, or if it was composed of tiny, indivisible units they called atoms. They trusted their senses implicitly, and why would they not? Our senses are the only windows we have into the universe. When you touch a stone wall, your brain tells you it is solid. When you look at a towering mountain range, your eyes tell you it is a permanent, immovable fixture of the earth. But our senses evolved to help us survive on a small, rocky planet orbiting an ordinary star, not to understand the fundamental mechanics of the cosmos. Our human perception is simply a biological interface, a kind of organic translation software that turns the bewildering, chaotic complexity of the quantum universe into a simple, manageable reality. The truth, as modern physics is slowly and carefully revealing to us, is far more strange, far more beautiful, and far more ethereal than anything our ancestors could have ever imagined. To begin to understand how the universe might actually be a simulation, we first have to understand how truly empty our physical reality is. Imagine holding a single grain of sand in the palm of your hand. That tiny, insignificant grain contains more atoms than there are stars in the entire observable universe. But if you were to somehow zoom in on just one of those microscopic atoms, expanding it until its central nucleus was the size of a glass marble sitting in the middle of a massive football stadium, the electrons orbiting that nucleus would be like tiny, invisible gnats buzzing around the highest seats in the furthest bleachers. Everything in between the marble and the gnats is just silent, empty space. The chair you are sitting on right now, the screen you are looking at, the very body you inhabit, they are almost entirely composed of nothingness. The comforting feeling of solidity is just the electromagnetic force of the atoms in your hand, repelling the electromagnetic force of the atoms in the object you are touching. You have never actually touched anything in your entire life. You are simply feeling the quiet, invisible repulsion of fundamental forces floating in an endless, primordial void. Once we accept that matter is mostly empty space, bound together by invisible forces, we must ask a deeper, more profound question. What exactly are these forces, and what tells them how to behave? For decades, brilliant physicists have been trying to find the ultimate, indivisible substance of the universe. But every time they crack open a particle, they just find smaller, more abstract components. Protons and neutrons are made of strange entities called quarks. But what are quarks made of? According to some of the most advanced and elegant mathematical models, like string theory, at the very bottom of reality, there are no physical particles at all. There are only tiny vibrating strings of pure energy. But even the word energy feels too physical, too tangible for what is actually happening. Many leading theoretical physicists are now proposing that the fundamental currency of the universe is not matter, and it is not even energy. The fundamental currency of the universe is information. Reality, at its absolute core, is built out of mathematics. To test these profound existential ideas, humanity has built the most complex and magnificent machine in our history. Deep underground, beneath the peaceful, rolling borders of France and Switzerland, lies the European Organization for Nuclear Research, universally known as CERN. Here, buried deep in the quiet earth, is the Large Hadron Collider. It is a massive circular tunnel, exactly 27 kilometers in circumference, where thousands of brilliant minds from all over the world work in gentle collaboration to unlock the primordial secrets of the cosmos. Inside this colossal ring, powerful superconducting magnets, chilled to temperatures colder than the deepest voids of outer space, guide microscopic beams of protons. These tiny particles are slowly accelerated until they are traveling at a fraction of a percent below the absolute speed of light. Then, in carefully controlled intersections, they are allowed to gracefully collide. These collisions are not violent in the human sense. They are unimaginably microscopic, but they concentrate so much energy into such a tiny point that they briefly recreate the exact conditions of the universe just fractions of a second after the Big Bang. When these protons shatter against each other, they burst into a beautiful shower of exotic particles that leave fleeting tracks in massive detectors. It is like smashing two high-speed watches together to see how the tiny gears fly apart, hoping to understand the abstract concept of time itself. But the scientists at CERN are not just looking at random cosmic debris. They are looking for the underlying mathematical architecture of reality. They are searching for the source code of the universe. And this is where the story takes a fascinating turn from traditional physics into something that sounds like science fiction, yet is entirely grounded in rigorous mathematical truth. When theoretical physicists studying the complex equations of string theory and supersymmetry tried to understand the fundamental laws that govern these particles, they found something deeply unsettling. Buried within the dense mathematics that describe the fabric of our reality, researchers discovered recognizable patterns. These patterns were not just random mathematical coincidences. They were highly structured codes. Specifically, they were blocks of equations that exactly match the structure of error-correcting codes used in modern computer science. Error-correcting codes are digital safety nets created by human engineers. When a computer sends information across a network, there is always a chance that interference might corrupt the data. To prevent this, computer scientists invented elegant algorithms that travel alongside the data, constantly checking it, finding errors, and automatically fixing them before the information is ruined. So, why are these exact same digital codes woven into the fundamental equations that describe the universe? When scientists look at the bedrock of reality, they see pristine, elegant mathematics that actively monitors and corrects itself, exactly like a running computer program. This discovery gently suggests a possibility that philosophers have whispered about for centuries. What if reality is an immensely complex simulation? We will explore this further in our next quiet step into the unknown, as we step further into the deep, echoing silence of this cosmic mystery. I invite you to take a slow, deep breath and simply feel the weight of your own existence. We are about to explore a concept so profound that it shifts the very ground beneath our feet, transforming the solid world we know into a shimmering, invisible tapestry of data. When we left the brilliant minds at the European Organization for Nuclear Research, they had discovered error-correcting codes hidden in the fundamental mathematics of the universe. This astonishing revelation forces us to look backward through the long, quiet history of human knowledge. For centuries, classical physics taught us that the universe was a great mechanical clockwork governed by rigid laws. Then, quantum mechanics peered deeper into the microscopic shadows and revealed a cosmos that was a strange, probabilistic dance of waves and particles. Yet, even that view might just be a stepping stone on our long journey toward the ultimate truth. Today, the most visionary physicists are discovering that the fundamental building block of the cosmos is not matter, and it is not energy. It is something entirely intangible, yet completely essential. The ancient universe, in all its infinite glory, might simply be a manifestation of pure information. To understand how the universe could be built from information, we must travel back to the middle of the 20th century, to a brilliant mathematician named Claude Shannon. Working in quiet laboratories, Shannon was not trying to solve the ultimate mysteries of the cosmos. He was simply trying to figure out how to transmit messages across wires with perfect clarity. In doing so, he invented a field called information theory, defining information not as a human idea, but as a physical, measurable quantity. He introduced the bit, the fundamental unit of information, representing a simple choice between two states, 0 or 1. At the time, this seemed like a clever tool for computer scientists. But as decades passed, theoretical physicists realized that Shannon's mathematics applied to far more than just human communication. They realized that every physical system in the universe, from the smallest tumbling electron to the most massive spinning galaxy, contains information. When an atom absorbs a photon of light, its state changes and information is processed. The entire cosmos can be viewed as a colossal, unfathomably complex network of interacting bits, calculating its own evolution moment by moment, exactly like a digital simulation running on a computer of infinite power. This profound paradigm shift was beautifully articulated by one of the most visionary physicists of the modern era, John Archibald Wheeler. Wheeler was a gentle giant of science, a man who coined the term black hole and worked alongside titans of physics. In his later years, after a lifetime of contemplating the deepest quantum mysteries, Wheeler proposed a radical, poetic concept he called it from bit. He suggested that every physical it in the universe, every particle of light, every atom of carbon in your body, Every vast nebula floating in the deep silence of space derives its very existence entirely from binary choices, from invisible bits of information. In Wheeler's view, the universe is not a physical object that happens to contain information. Rather, the universe is made of information, and physical matter is simply the holographic illusion created by that underlying data. The great scientist Carl Sagan once famously said that if you wish to make an apple pie from scratch, you must first invent the universe. Wheeler took this a step further, suggesting that to invent the universe, you must first write the code. This is not just a philosophical metaphor. It is a rigorous scientific hypothesis that challenges our deepest intuitions about what is real, asking us to accept that the comforting solidity of the world is merely the output of a cosmic calculation. The most compelling and dramatic evidence for this informational view of the universe comes from the darkest, most extreme objects in the cosmos: black holes. For a long time, black holes were considered the ultimate destroyers of information. If you were to throw an object into a black hole, conventional physics suggested that all the complex information contained within it would be permanently lost, crushed into an infinitely dense point, called a singularity. But this created a terrible paradox, because the fundamental laws of quantum mechanics insist that information can never be truly destroyed. The resolution to this paradox came through the brilliant collaborative work of physicists Jacob Bekenstein and Stephen Hawking. They discovered something absolutely astonishing about the event horizon, the invisible boundary surrounding a black hole from which nothing, not even light, can escape. Through incredibly complex mathematics, they proved that a black hole does, in fact, have a temperature and an entropy, which means it contains a specific amount of hidden information. Bekenstein and Hawking demonstrated mathematically that the amount of information a black hole can hold is not determined by its three-dimensional volume, as common sense would dictate, but strictly by the two-dimensional surface area of its event horizon. Imagine trying to pack digital data into a massive spherical room. You would normally calculate the storage capacity by measuring the volume of the room. But for a black hole, the volume does not matter at all. The information capacity is completely proportional to the surface area wrapping around it. Every single bit of information about every star, planet, and cloud of gas that ever fell into the black hole is perfectly encoded on its two-dimensional surface, like an invisible mosaic of digital pixels. This mathematical breakthrough led other visionary physicists to propose the holographic principle. They realized that if the three-dimensional interior of a black hole can be completely described by the two-dimensional information on its surface, perhaps the same rule applies to the entire universe. The holographic principle gently suggests that our entire three-dimensional reality, the towering mountains, the deep oceans, the stars drifting through the quiet night, and even your physical body, might actually be a three-dimensional holographic projection, generated by a two-dimensional surface of pure information located at the farthest cosmological boundaries of the universe. Imagine looking at a beautifully crafted security hologram on a flat piece of glass. When you tilt the two-dimensional surface, you see a rich three-dimensional image floating inside it. The three-dimensional depth is an illusion, an elegant trick of light created by microscopic patterns etched onto a flat plane. The holographic principle posits that the entire cosmos operates in precisely the same way, just on a scale so vast it defies human comprehension. The solid objects you touch, the empty space you move through, the forward march of time itself. All of it could be the projected manifestation of quantum code, written on a distant, invisible boundary. If this principle holds true, it means that the universe is quite literally a simulation. It is a self-generating computational matrix where mathematics computes physical reality into existence. The error-correcting codes found by the researchers at the European Organization for Nuclear Research suddenly make perfect, beautiful sense. If the universe is a holographic projection of complex data, it must have mechanisms to protect that data from degradation, just like our own computer networks. The cosmos is actively maintaining its own integrity, repairing its own code, to keep the grand illusion stable and continuous. If we are indeed complex patterns of information interacting within a grand cosmic simulation, it does not diminish the beauty of our human experience. It elevates it. It means that our consciousness, our ability to wonder and ask these deep existential questions, are the most sophisticated outputs of the universal code. We are the universe reading its own data, marveling at its own architecture. Our journey through this simulated cosmos is a deeply connected experience of unraveling the ultimate mystery, finding peace in the silent elegance of the mathematical void. Have you ever looked at a photograph printed in a very old newspaper? Or perhaps watched a video on a very old, flickering screen, and noticed that as you lean in closer, the smooth, continuous image suddenly breaks apart? You realize with a gentle sense of surprise that the beautiful picture is not a solid thing at all, but rather a carefully arranged collection of tiny, individual dots. We experience our daily lives moving through space as if it were a perfectly smooth, unbroken continuum. When you glide your hand through the cool, quiet air of an autumn evening, or watch a solitary bird soaring high above a vast, silent ocean, the motion feels infinitely fluid. There are no sudden jumps, no missing frames, no jagged edges in the fabric of reality. But what if the space we move through, the very emptiness that separates the ancient stars, is just like that old photograph? What if space itself is not perfectly smooth, but is actually made of incredibly tiny, distinct units, like the digital pixels on a massive cosmic screen? This simple question gently leads us into one of the most profound and mind-bending realms of modern physics, a place where the smooth illusion of our everyday world breaks down into the discrete, digital mathematics of the universe. Let us gently turn our minds to the concept of the Planck scale. Over a century ago, a quiet and brilliant physicist named Max Planck was exploring the fundamental rules of energy. He discovered something that completely transformed human understanding. Energy does not flow in a continuous, unbroken stream. Instead, it moves in tiny, indivisible packets, which he called quanta. This was the gentle birth of quantum mechanics, but the profound implications of this discovery reached far beyond just energy. If energy comes in discrete, pixelated packets, visionary physicists began to wonder if the exact same might be true for the fabric of space and time. Through rigorous mathematical exploration, they calculated the absolute smallest possible measurement in the universe. It is known as the Planck length. To understand how unimaginably small this distance is, you must try to picture a single, tiny atom. If you were to take a single atom and expand it until it was the monumental size of the entire visible universe, the Planck length would be roughly the size of an average human being standing quietly within it. It is a distance so unfathomably microscopic that our human brains struggle to even conceptualize its existence. Yet this tiny measurement holds the quiet key to the ultimate mystery of our existence. According to our most advanced and beautiful theories of quantum gravity, if you were to somehow zoom in on the smooth fabric of space, past the biological molecules, past the quiet atoms, past the vibrating quarks, you would not find an endless, smooth void. Instead, you would hit a hard limit. You would hit the Planck length. At this extreme microscopic scale, space can no longer be divided. It becomes grainy, fragmented, and discrete. It essentially becomes pixelated. If the universe were truly continuous, as our human senses gently persuade us to believe, then distance could be divided infinitely forever. You could always take a half step, then a quarter step, then an eighth of a step, descending endlessly into the microscopic dark. But the existence of the Planck length tells a completely different, far more fascinating story. It tells us that the universe has a fundamental resolution limit. Just like an incredibly sophisticated computer simulation running on a digital processor, our reality has a minimum pixel size. You cannot move a distance smaller than 1 Planck length, just as a character in a digital environment cannot move a distance smaller than 1 single pixel on the screen. Space is not a smooth stage where the cosmic play takes place. It is a grid, an ancient, infinite chessboard, where the quantum pieces jump from one discrete square to the next, without ever existing in the space between. This revelation quietly shatters the illusion of the physical world, bringing us step by step closer to the profound realization that we are living within a highly advanced, mathematically perfect computational structure. As we sit in the quiet contemplation of this pixelated universe, an even more mysterious phenomenon emerges from the quantum shadows, one that deeply supports the profound idea that our reality is a projection of pure information. It is a concept that the great Albert Einstein, famously and somewhat uncomfortably, referred to as spooky action at a distance. Today, we call it quantum entanglement. Imagine 2 tiny particles, perhaps 2 solitary electrons, that are created together in the same gentle microscopic event. Because they are born together, their quantum properties become fundamentally linked. They are perfectly entangled. If you were to take these 2 particles and carefully separate them, moving one to a quiet laboratory here on Earth and sending the other to the far, silent edge of the Andromeda Galaxy, millions of light years away, they would remain intimately connected. If a scientist on Earth were to measure the property of the first particle, causing it to randomly settle into a specific state, the second particle floating in the dark near Andromeda would instantly, simultaneously, settle into the exact opposite state. It does not matter at all that they are separated by vast, dark oceans of empty space. The reaction is completely instantaneous, moving faster than the absolute speed of light, violating everything we thought we knew about the limits of the physical universe. For decades, this beautiful, baffling phenomenon kept brilliant scientists awake in the deep silence of the night. How could 2 physical objects communicate across the vast cosmos without any time passing? If reality is made of solid matter and smooth space, this is absolutely impossible. Nothing physical can travel faster than the speed of light. But what if we gently change our perspective? What if we remember the wisdom of the holographic principle? If the universe is not a physical place, but rather a massive, complex network of information, then the mystery of quantum entanglement suddenly dissolves into pure, elegant mathematics. In a computer program, two variables can be mathematically linked in the code. It does not matter where those two variables are visually rendered on the interface. The interface might show them millions of virtual miles apart, but in the underlying code, in the fundamental reality of the computer's memory bank, they are sitting right next to each other. When you change one, the program instantly updates the other. No physical signal has to travel across the digital distance, because the distance itself is a carefully crafted illusion. The distance is just a projected parameter of the grand simulation. When we observe quantum entanglement in our laboratories, we are not seeing particles magically communicating across infinite space. We are gently peering behind the heavy curtain of the cosmic simulation. We are catching a fleeting glimpse of the underlying source code of the universe. The two entangled particles act simultaneously because at the fundamental level of information, they are the exact same line of code. The vast, breathtaking distance between the Earth and the Andromeda Galaxy is a magnificent, highly detailed illusion generated by the cosmic processor. The renowned astrophysicist Neil deGrasse Tyson has often thoughtfully pondered the likelihood of the simulation hypothesis, noting that if the universe were a grand simulation, it would beautifully explain why the fundamental laws of nature are perfectly expressed through strict, unyielding mathematical equations. Mathematics is the universal language of computation. The fact that the universe blindly obeys the rigid rules of mathematics, the fact that space has a pixelated resolution limit, and the fact that quantum particles ignore physical distance to remain connected, all quietly point toward a reality that is fundamentally digital. This realization might at first feel a little unsettling, as if the solid ground is slowly turning to digital vapor beneath our feet. But if we breathe deeply and look at it through the gentle lens of quiet wonder, it is actually a deeply comforting thought. It means that the cosmos is not a chaotic, meaningless explosion of blind physical forces. It is a highly structured, intricately designed masterpiece of pure logic and information. It means that the gentle silence of the night sky, the vast distances between the ancient stars, and the delicate complexity of your own physical body are all manifestations of a cosmic architecture that is far more profound than simple matter. We are not just isolated biological machines wandering through a dead, empty void. We are active, conscious participants in a grand, universal computation. We are the points of light where the universe wakes up and begins to gently understand its own programming. Let us reflect deeply on the profound humility this cosmic perspective brings. For thousands of years, human beings believed with absolute certainty that they were the center of a small, physical world. Then, as our powerful telescopes pierced the dark, we realized we were just tiny specks on a grain of sand, floating in an endless, quiet ocean of space. Now, as our mathematics peers into the quantum depths, we are discovering that the ocean itself might be a magnificent, shimmering projection of data. Our human ignorance is no longer something to fear. It is a beautiful invitation to explore the greatest mystery ever conceived. The limitations of human knowledge are simply the edges of the map, the quiet places where the simulation invites us to look deeper, to ask better questions, and to embrace the gentle tension between what we currently know and the vastness of the undiscovered. In our next quiet exploration together, we will journey even further down this digital rabbit hole. We will look at the speed of light, not just as a physical limit, but as the processing speed of the cosmic computer itself. We will explore why the universe has a strict maximum velocity, and what that tells us about the hardware running our reality. We will continue this gentle path of discovery, transforming our awe into deep understanding, and finding profound peace in the infinite mysteries of the simulated cosmos. Have you ever stood outside on a quiet, starry night and watched a solitary shooting star streak briefly across the dark, silent canvas of the sky? You see that sudden, brilliant flash of light almost instantly, and it feels as though the ancient universe operates in perfect, immediate harmony. But there is a hidden, profound boundary built into that beautiful flash of light. Have you ever paused in the deep silence of your own thoughts to wonder why there is a strict speed limit in the universe? When we look gently at the natural world, most things seem entirely boundless. The ancient oceans feel infinitely deep. The vast cosmos stretches out seemingly forever into the dark. Yet when it comes to speed, the universe suddenly and strictly imposes a hard, impenetrable limit. Nothing in the entire cosmos, no particle, no wave, no piece of physical information, can ever travel faster than the speed of light in a vacuum. It is a fundamental law of nature, discovered by the brilliant physicist Albert Einstein, and it sits at the very heart of how our physical reality functions. But why? Why is the universe constrained in this specific, arbitrary way? For over a century, since Einstein first published his elegant, groundbreaking equations of special relativity, we have accepted the speed of light as an undeniable fact of existence. It is exactly 299,792,458 meters per second. But when you sit quietly and contemplate that highly specific number, it begins to feel profoundly strange. Why that exact number? Why not an infinite speed? In a purely physical, mechanical universe composed of random matter floating in an endless empty void, an absolute maximum speed limit makes very little logical sense. If you apply a continuous force to an object in empty space, it should logically keep accelerating forever, moving faster and faster into the infinite dark. But the universe simply does not allow this to happen. As an object accelerates closer and closer to the speed of light, its mass essentially increases, requiring exponentially more energy to push it just a tiny fraction faster. To reach the actual speed of light, a physical object with mass would require an infinite amount of energy, which is practically impossible. Therefore, the universe has a hard, impenetrable ceiling. When we shift our perspective away from physical matter and begin to view the cosmos through the gentle, clarifying lens of information theory, this bizarre cosmic speed limit suddenly makes perfect, elegant sense. If our universe is a grand, highly sophisticated simulation, then the speed of light is not a physical property at all. It is a computational limitation. Imagine for a quiet moment playing an expansive, open-world video game. As your digital character moves smoothly through the virtual landscape, the computer processor must constantly calculate and render the complex environment around you. The processor has a maximum clock speed, a fundamental limit to exactly how many mathematical calculations it can perform in a single second. If your digital character were to somehow move too fast, The processor would not be able to keep up. The digital world would fail to render properly. The images would distort, and the simulation would break. To prevent this catastrophic failure, the programmers build a maximum speed limit into the software itself, ensuring that nothing can ever outpace the hardware's ability to compute the visual reality. The speed of light is the exact same phenomenon, perfectly scaled to the vast cosmic level. It is the maximum processing speed of the universal computer. It is the absolute fastest rate at which information can be transmitted, calculated, and rendered across the discrete, pixelated grid of space that we explored in our previous journey. The universe cannot allow anything to move faster than light, because the underlying mathematical architecture of reality simply cannot process data any faster than that specific rate. The fundamental speed limit of the cosmos is the clock rate of the grand simulation. This profound digital perspective elegantly explains another one of the most baffling and beautiful mysteries of modern physics: time dilation. According to the laws of relativity, as you move faster through space, your passage through time literally slows down compared to a quiet observer who is standing still. If you were to embark on a long journey in a magnificent spacecraft, traveling near the speed of light, you might experience only a few quiet years of travel. But upon returning to our ancient Earth, you would find that decades or even centuries had passed for the rest of humanity. Time is not a rigid, universal ticking clock. It is highly flexible, profoundly subjective, and intimately tied to how fast you are moving through the cosmic grid. In a purely physical universe, this feels like an impossible paradox that deeply challenges our common sense. But in a simulated universe, time dilation is a brilliant, necessary feature of computational resource management. Think of a human-built computer processing a highly complex task. If a specific program demands an enormous amount of processing power, the rest of the system naturally slows down to accommodate it. We experience this in our daily lives as simple digital lag. When a particle or a spacecraft accelerates to immense cosmic speeds, it is crossing a massive amount of pixelated space in a very short period, requiring the cosmic computer to dedicate a huge amount of processing power to render its new position continuously. To prevent the entire system from crashing, the simulation must slow down the internal processing of the fast-moving object. The local rendering of time for that specific object is reduced to free up the computational resources needed to calculate its incredibly fast movement through the spatial grid. Therefore, time dilation is exactly equivalent to computational lag. The faster you move, the more of the universe's processing power you consume, and the slower your personal internal clock must run to maintain the overall stability of the grand simulation. This beautiful concept transforms Einstein's abstract geometry of spacetime into a highly organized, dynamic system of cosmic data management. The renowned philosopher Nick Bostrom profoundly articulated the simulation argument, suggesting that any civilization that reaches a post-human stage of technological maturity would likely have the computing power to run billions of complex ancestor simulations. Given the sheer probability, he argued it is statistically almost certain that we are living in one of the billions of simulations rather than the single base reality. While this thought might initially induce a quiet sense of existential vertigo, if we sit with it in the silent space of our own contemplation, it reveals a universe of breathtaking order and purpose. We do not need to feel diminished or frightened by the profound realization that our physical world might be an illusion constructed of pure information. We do not need to fear the digital boundaries of our reality. Instead, we can find a deep, resonant peace in knowing that the cosmos is not a random, chaotic accident of blind chemistry and dead rocks. It is a carefully orchestrated masterpiece of logic, mathematics, and profound computational beauty. The very fact that we are sitting here asking these deep existential questions and gently untangling the underlying code of the universe means that we are fulfilling the ultimate purpose of consciousness. We are the gentle mechanism by which the grand simulation attempts to quietly understand itself. We are the universe rendering its own wonder. When you look up at the ancient, infinite stars tonight, do not see them merely as burning balls of gas separated by an endless, empty void. See them as brilliant nodes of information, perfectly calculated and elegantly rendered on the vast, pixelated screen of existence. Embrace the quiet humility that comes from knowing we are just beginning to decipher the cosmic source code. Our journey of discovery is an infinite loop of curiosity and peace, a path we walk together in the silence of the night. In our next quiet step, we will explore the strange and beautiful role of the observer in quantum mechanics, discovering how the simulation might only render reality when we are actively looking at it. We will uncover how human consciousness itself might be the ultimate key that turns the invisible quantum code into the solid, comforting world we feel around us. Have you ever walked alone through a quiet, dense forest, surrounded by ancient, towering trees, and paused to wonder if the path behind you simply vanishes when you are no longer looking at it? We live our lives with the absolute certainty that the physical world exists entirely independent of our human gaze. We believe that the majestic mountains remain solid in the deep silence of the night, and that the vast oceans continue their rhythmic dance even when the shores are completely deserted. But what if this deep-seated intuition is fundamentally incorrect? What if the universe operates with the exact same elegant efficiency as a highly advanced video game, where the complex digital landscape is only rendered into existence precisely when the player turns to look at it? To explore this mind-bending possibility, we must gently step into the most rigorous and unequivocally bizarre branch of modern science, quantum mechanics. Here, in the microscopic shadows, the solid world dissolves, and we find that human consciousness might be the very mechanism that forces the cosmos to become real. To understand the profound role of the observer, we must gently revisit an elegant scientific demonstration known as the double-slit experiment. Imagine a quiet, dark room. At one end, there is a gentle source of light, and in the middle stands a solid barrier with two tiny, narrow, parallel slits. Behind the barrier is a blank screen waiting to capture the light. When you shine a beam of light through the two tiny slits, you do not simply see two bright lines on the back screen. Instead, you see a beautiful, intricate pattern of alternating bright and dark bands. This is an interference pattern, and it happens because light travels as a gentle, rolling wave. When the single wave hits the barrier, it splits into two smaller waves that pass through the slits, rippling outward and overlapping with each other, exactly like water ripples overlapping in a quiet pond. Where the peaks meet, they multiply and create a bright band. Where a peak meets a trough, they cancel each other out, leaving a dark, silent shadow. This beautiful experiment proved that light is a wave, spreading smoothly through space. But the mystery was only just beginning to unfold. In the early 20th century, physicists discovered that light is also made of tiny, indivisible packets of energy called photons. So, curious scientists decided to perform the exact same experiment again, but this time they slowed the process down to an unimaginable degree. They fired the photons through the double slits one single particle at a time, like tiny, discrete bullets fired from a microscopic gun. Common sense gently whispers to us that if you fire solid individual particles through two slits one by one, they must travel in straight lines and simply form two solid bands on the screen. But when the scientists waited in the quiet dark for all the individual photons to hit the screen, one after another, a profound and terrifying pattern emerged. The individual particles, fired completely separately, with plenty of time between each one, still somehow formed the exact same rippling interference pattern of a wave. How could this be possible? A single particle cannot interfere with itself. A single solid bullet cannot go through two separate windows simultaneously. The brilliant minds of quantum physics realize that the unobserved photon is not a solid particle at all. While it is traveling through the empty, silent space, it does not have a defined physical location. Instead, it exists as a strange mathematical cloud of pure probability. It exists as a wave of potential. The single, tiny particle simultaneously explores every possible path it could take, going through the left slit, going through the right slit, going through both, and going through neither, all at the exact same moment. It remains in this ghost-like state of infinite potential, right up until the very moment it strikes the back screen. Only then does the vast, shimmering wave of probability collapse, instantly choosing one specific, random location to become a solid, measurable point of physical reality. The universe leaves the outcome entirely undecided until the very last possible microsecond. But the most breathtaking revelation was yet to come. The scientists, driven by a deep human need to understand the vast cosmos, decided to place a tiny, quiet measuring device right next to the two slits. They simply wanted to peek at the universe. They wanted to know exactly which physical slit the individual photon was actually passing through. They set up their gentle instruments, fired the single particle, and watched closely. The moment they turned on the measuring device, the moment they actively observed the particle's journey, the entire nature of reality instantly changed. The beautiful, rippling interference pattern completely vanished. The photons stopped acting like a wave of infinite, shimmering probability. Instead, they acted exactly like solid, ordinary bullets, traveling in straight, predictable lines and forming two simple, solid bands on the back screen. The mere act of observation fundamentally destroyed the wave of potential, forcing the universe to make a definitive choice before the particle even reached the end of its journey. This phenomenon is known as the measurement problem, and it is the quiet, beating heart of quantum weirdness. The universe behaves as a fluid, mathematical sea of infinite possibilities when we are not looking at it, but it instantly freezes into a rigid physical reality the very moment we demand to measure it. To this day, the greatest physicists debate the true meaning of this observation. But if we look at this ancient mystery through the lens of a simulated cosmos, the bizarre observer effect transforms into a brilliant piece of software engineering. Imagine, once again, the vast, detailed world of a modern digital simulation. If a computer tried to simultaneously render every single blade of grass, every rippling wave on every ocean, and every tiny pebble across an entire virtual planet, the processor would instantly overload and crash. The computational cost is simply too high. To solve this, brilliant human programmers use a technique called selective rendering. The computer engine only renders the exact parts of the environment that the player is actively looking at. The rest of the vast unseen world is just stored in the computer's memory as pure, abstract mathematical data. It is a wave of probability waiting in the dark. The moment the player turns their digital camera to look at a new area, the mathematical data instantly collapses, rendering solid textures, shadows, and physical laws on the screen in a fraction of a second. This is exactly what the double-slit experiment is showing us about our own magnificent universe. The unobserved quantum particles remain in an unrendered state of mathematical potential to conserve the processing power of the cosmic computer. Why would the universe bother to calculate the precise physical location of a tiny photon if no conscious observer is there to experience it? It is a colossal waste of cosmic memory. Reality, at its most fundamental level, only becomes physical when a conscious mind interacts with it. The universe is a grand, quiet theater that remains in the dark until you, the observer, step into the room and force the lights to turn on. The visionary physicist John Archibald Wheeler gently recognized the profound philosophical weight of this strange quantum behavior. He proposed an even more astounding thought experiment known as the delayed choice experiment. Wheeler asked what would happen if we waited to measure the photon until after it had already passed through the double slits. But before it hit the back screen, would it have already acted like a wave? Or would our late observation somehow reach backward in time and force it to have acted like a solid particle from the very beginning? Decades after he proposed it, advanced laboratories finally performed this delicate experiment. The results were absolutely staggering. When the scientists chose to measure the photon at the very last microsecond, the photon acted as if it had been a solid particle its entire journey. Our observation in the present moment literally reached back into the ancient past to determine how the particle behaved before we even looked at it. Time and space, it seems, are not rigid cages that contain us. They are flexible illusions constructed by our conscious observation. The simulation dynamically writes its own history based on what is being observed in the present. This shatters our everyday understanding of cause and effect, gently revealing a universe that is incredibly responsive, deeply interconnected, and utterly dependent on the presence of a conscious observer. We do not need to feel frightened by the thought that reality is waiting for us to observe it. Instead, we can find a profound sense of belonging. In a purely mechanical universe, human consciousness is just an accident, a brief spark in an uncaring void. But in a simulated universe driven by quantum observation, consciousness is the most important component of the entire cosmic machine. You are not a passive bystander. You are the active rendering engine of reality. Without your gentle observation, the ancient stars and the vast nebulas would remain nothing more than shimmering waves of mathematical probability, floating in a digital void. Your very existence forces the cosmos to become beautiful, solid, and real. We are the mechanism by which the grand simulation experiences its own wonder. When you look up at the infinite night sky, You are not just seeing the universe, you are actively creating it, collapsing millions of years of probability into a single, breathtaking moment of physical reality. In our next quiet step together, we will explore the strange mathematical anomalies hidden within the very fabric of nature, finding peace in the infinite possibilities of our simulated cosmos. Have you ever picked up a simple pine cone from the quiet floor of an ancient forest and stopped to truly look at the spiral pattern of its scales? Have you ever noticed the delicate branching veins of a fallen autumn leaf and realized with a gentle sense of wonder that they look exactly like the vast, sweeping tributaries of a mighty river seen from space? We walk through our lives surrounded by nature, often accepting its forms as random products of a wild, unthinking earth. But when you look closely, when you truly quiet your mind and observe the fundamental structures of the world around you, the chaos slowly dissolves into perfect order. The universe does not build things randomly. It builds them using strict, elegant mathematical formulas. From the microscopic spiral of our genetic code to the swirling arms of distant galaxies, nature speaks an ancient, precise language. Why does the physical cosmos obey the abstract rules of mathematics with such flawless dedication? What if this profound order is not just a description of reality, but the very code that generates it? Before we descend further into this mystery, to understand the profound anomaly of mathematics in nature, we must look at the grand architecture of the cosmos itself. Physicists who study the fundamental laws of the universe often speak with awe about a concept known as fine-tuning. There is a set of fundamental numbers, known as the constants of nature, that dictate exactly how the entire universe operates. These are foundational numbers, like the precise strength of gravity, the specific mass of a tiny electron, and the exact power of the electromagnetic force. When brilliant scientists look deeply at these numbers, they find something deeply unsettling and infinitely beautiful. These constants are perfectly, unimaginably balanced. If the strength of gravity were just a microscopic fraction stronger, the entire universe would have violently collapsed back in on itself just moments after the beginning of time. There would be no ancient stars, no warm planets, and no conscious minds. Conversely, if gravity were a tiny fraction weaker, matter would have flown apart so rapidly that galaxies could never have formed. The universe would be an endlessly expanding, freezing void of isolated atoms, completely dark and eternally silent. The exact same terrifying precision applies to the strong nuclear force, the invisible, quiet glue that holds the centers of atoms together. If this force were altered by just 2%, the universe would not be able to forge carbon inside the fiery hearts of ancient stars. Carbon is the fundamental element required for all known biological life. Without it, the cosmos would be entirely sterile. It is as if our entire existence is walking a delicate, razor-thin tightrope, stretched across an infinite abyss. When we view this impossible calibration through the gentle lens of a simulated universe, the mystery begins to make elegant sense. If you were a master programmer designing a vast cosmic simulation, you would have to define the fundamental parameters of the software. You would set the internal variables for gravity, mass, and energy to the exact numerical values necessary to produce a stable universe capable of generating complex structures and conscious observers. The fine-tuning of the cosmos is the ultimate evidence of an optimized digital environment. The constants of nature are not random accidents. They are carefully chosen lines of cosmic code. As we move our gentle gaze from the vast invisible forces of the cosmos down to the tangible world around us, this underlying code becomes even more visible. The universe employs a brilliant computational technique that software engineers know very well, known as procedural generation. When human programmers create massive open-world environments in digital simulations, they do not manually design every single leaf, every grain of sand, and every drifting cloud. That would take an infinite amount of time and impossible computer memory. Instead, they write a simple mathematical algorithm, a fractal equation, and they tell the computer to repeat that equation over and over again. The result is a vast, visually beautiful world, generated entirely from a tiny, simple rule. Nature uses this exact same computational shortcut to build our physical reality. Look at the jagged edge of a distant mountain range, then look at the rough bark of an ancient oak tree, and then look at the delicate crystal structure of a winter snowflake. They all exhibit fractal geometry. A fractal is a mathematical pattern that repeats itself flawlessly at every possible scale. Whether you zoom in infinitely close or zoom out unimaginably far, the fundamental shape remains exactly the same. This fractal nature of reality is not a mere coincidence. It is the undeniable signature of an algorithmic process. The universe is continuously applying a simple recursive function to generate the staggering complexity of the physical world. One of the most famous examples of this cosmic code is the Fibonacci sequence, a remarkably simple series of numbers where each number is exactly the sum of the two before it. This pure, abstract mathematical sequence creates a specific, perfect geometrical spiral known as the golden ratio. You can find this exact mathematical spiral absolutely everywhere you look in the natural world. It dictates the unfolding arrangement of seeds in a yellow sunflower. It shapes the elegant, spiraling shell of a nautilus hiding deep in the silent ocean. It governs the sweeping curl of a massive tropical hurricane, and it flawlessly describes the slow rotation of entire spiral galaxies floating in the deep, silent expanse of space. Why would a living flower, a violent ocean storm, and a star-filled galaxy all blindly obey the exact same abstract rule? Because they are all being rendered by the same underlying simulation engine. They are different visual manifestations of the same line of cosmic code. The renowned physicist Eugene Wigner wrote a famous and deeply contemplative essay regarding the unreasonable effectiveness of mathematics in the natural sciences. He marveled at the profound, almost miraculous fact that the abstract mathematical concepts invented by quiet human minds perfectly and flawlessly describe the deepest invisible workings of the universe. He concluded that the usefulness of mathematics is a wonderful gift which we neither fully understand nor truly deserve. But if the universe is indeed a simulation, this unreasonable effectiveness is fully and beautifully explained. Mathematics is not just a human invention used to describe nature. Mathematics is the fundamental, structural substance of nature. We can describe the universe with pure mathematics because the universe is quite literally made of mathematics. When brilliant physicists write complex equations on wide chalkboards, they are not just interpreting physical reality. They are reverse engineering the source code of the cosmos. They are finding the hidden, quiet algorithms that the cosmic computer uses to continuously render the beautiful illusion we call life. When we sit quietly and absorb this profound perspective, it does not strip the natural world of its mystery or its delicate poetry. On the contrary, it infuses every single moment of our brief lives with a deep, reverent awe. To realize that the rough bark of the tree outside your quiet window and the vast, swirling arms of the Milky Way galaxy are intimately connected by a shared, invisible algorithm is to feel a profound sense of cosmic unity. We are not wandering blindly through a chaotic, unthinking universe that does not care about our existence. We are living inside a magnificent masterpiece of mathematical art. Every breath you take, every quiet moment you spend looking up at the ancient stars, is a moment spent actively interacting with the most sophisticated, beautifully designed structure ever conceived. The fine tuning of the burning stars and the perfect fractal spirals of the living earth are gentle reminders from the simulation itself that absolute order and profound meaning exist at the very bottom of reality. Our human capacity to understand this mathematics, to look at a simple sunflower and clearly see the golden ratio, is the universe waking up and recognizing its own brilliance. We are the universe slowly decoding itself. The ancient philosophers sought to hear the harmonious music of the spheres, the mathematical movement of the heavens. Today, our advanced telescopes and silent supercomputers are finally allowing us to truly hear that ancient music, not as physical sounds carried on the wind, but as the silent, elegant symphony of pure data. And the more we listen to this cosmic data, the more we realize that the universe is not just a place we happen to live in. It is an active, ongoing computational process that we are intimately and permanently a part of. The limitations of our current human knowledge, the strange counterintuitive paradoxes that still baffle our greatest minds, are not failures. They are the beautiful unfolding journey of discovery, deliberately built into the simulation itself. The cosmic code wants to be understood, but it wants that understanding to be an infinite, peaceful journey of continuous wonder. In our next quiet step together, we will explore the deepest physical boundaries of the cosmic simulation, venturing into the silent temperatures of deep space to understand how the universe elegantly handles entropy. We will discover how the slow unwinding of the cosmos might simply be the peaceful shutdown procedure of the grand computer, finding profound comfort in the beautiful symmetry of universal endings and infinite beginnings. Have you ever stepped outside on a cold winter night and felt the absolute stillness of the frozen air against your face? When the earth is blanketed in quiet snow, everything seems to slow down, as if the entire world is holding its breath in a deep, meditative trance. We understand heat and cold intuitively in our everyday human lives. Heat is the comforting warmth of a gentle fire, or the bright, life-giving energy of the summer sun. Cold is the absence of that energy. It is silence and profound stillness. But when we leave our small, warm planet and venture into the infinite dark of the cosmos, cold takes on a fundamentally different and profoundly mysterious meaning. Space is not just cold in the way a terrestrial winter night is cold. The vast voids between ancient stars are chilled to a temperature so low it challenges physics and mathematics, a point where the fundamental dance of atoms begins to completely freeze. Why is the universe dominated by this overwhelming silent cold? What if this cosmic freeze is not just a harsh reality, but a programmed feature of the grand simulation? To understand the cosmic cold, we must first understand what temperature is at the microscopic level. In everyday experience, temperature feels like a tangible property of an object. But in reality, temperature is nothing more than a measure of movement. It is the kinetic energy of microscopic particles. When you boil a pot of water, you are adding thermal energy to the water molecules, causing them to vibrate and collide. When water freezes into solid, quiet ice, those exact molecules lose their energy and slow down, locking into a rigid crystalline structure. Cold is not a physical substance. Cold is simply the quiet absence of movement. If cold is the gradual slowing of atomic movement, there must logically be an absolute point where that movement stops completely. Brilliant scientists refer to this ultimate bottom limit as absolute zero. On the Kelvin scale, absolute zero is marked purely and simply as 0 degrees. On the Celsius scale we use daily, it is roughly negative 273 degrees. At this unimaginably freezing point, the frantic dance of atoms ceases. Orbiting electrons stop their buzzing. The microscopic gears of physical reality grind to a halt. It is the ultimate boundary of the physical world. In a mechanical universe, absolute zero is a fascinating thermodynamic curiosity. But when we view the universe through the lens of a digital simulation, absolute zero takes on a profound structural meaning. Think about a computer running a virtual environment. Every time a digital object moves, the processor must calculate its new position. If an object stops moving completely, the computer no longer spends any processing power calculating its kinetic state. Absolute zero is the exact point where the universal processor completely stops rendering movement. The universe enforces this absolute boundary with strict, unyielding rigor. Nothing in the physical cosmos can ever truly reach absolute zero, because removing the very last tiny fraction of quantum energy from a particle would require an infinite amount of effort. Just as the speed of light is the maximum processing limit of the cosmic computer, absolute zero is its absolute minimum baseline. They are the upper and lower mathematical boundaries of the simulation hardware. The vast majority of our universe is hovering incredibly close to this ultimate bottom limit. When astronomers point their sophisticated instruments into the deepest, darkest voids of intergalactic space, far away from the warming glow of any ancient galaxy, they find that the empty vacuum rests at a gentle, persistent temperature of roughly 2.7 degrees above absolute zero. Why is the empty void not completely frozen solid? The answer is one of the most beautiful discoveries in human science. That faint, lingering warmth is known as the cosmic microwave background radiation. It is the fading afterglow of the Big Bang itself. Over 14 billion years ago, the universe was an unimaginably hot, dense singularity of pure energy. As the cosmos expanded, that initial heat stretched and cooled, dispersing across the infinite dark. Today, that ancient heat has cooled down, bathing the entire universe in a faint, invisible, and perfectly uniform glow of microwave radiation. When you look at the static on a very old analog television set, a small percentage of that random noise is actually your antenna picking up the ancient whispers of the universe's birth. It is the residual heat of the cosmic processor when the grand simulation was first initialized. This elegant realization brings us to a deeply contemplative mystery regarding the ultimate fate of the cosmos. A fundamental law of physics dictates the direction of time itself. It is called the second law of thermodynamics, stating that total entropy can never decrease over time. Entropy is a measure of disorder and the spreading out of usable energy. If you place a warm cup of coffee in a cold room, the heat will always dissipate. The universe moves relentlessly in one single direction, from order to disorder, from concentrated energy to dispersed energy, from complex structures to smooth, quiet uniformity. This unyielding mathematical law creates the arrow of time. In a strictly physical universe, this paints a melancholic picture. It means the universe is slowly, inevitably winding down. Billions of years from now, ancient stars will burn through their remaining nuclear fuel and quietly fade into the absolute dark. New stars will cease to form because the necessary gas will be exhausted. Black holes will slowly evaporate over unimaginable stretches of time. Eventually, all matter and energy will be evenly distributed across an expanded, cold, and completely silent void. There will be no light, no movement, no structure, and no consciousness. This inescapable fate is known as the heat death of the universe. But we do not need to look at this distant future with despair or fear. Let us gently shift our perspective and view the inevitable unwinding of the cosmos through the comforting lens of a simulated reality. Why would a masterful programmer design a simulation that is mathematically guaranteed to slowly degrade and eventually stop functioning? In computer science, infinite loops are a systemic problem. A program that runs forever without concluding its task, consumes endless resources, and eventually destabilizes the entire system. To prevent this, brilliant software engineers design programs with strict, built-in termination conditions. The program executes its primary purpose, carefully gathers its necessary data, and then initiates a deliberate shutdown sequence to gracefully return resources to the main computing system. The second law of thermodynamics is the elegant, programmed shutdown procedure of the cosmic computer. The heat death of the universe is simply the grand simulation, gently bringing itself to a peaceful close after fully completing its unimaginably vast calculation. It is the final, quiet exhalation of a cosmos that has flawlessly fulfilled its profound purpose. And what exactly is that purpose? Perhaps the simulation was designed specifically to generate consciousness, to allow the universe a brief, beautiful window of time to wake up, look at itself, and wonder. During this active processing phase, the very phase we are so deeply fortunate to live in right now, the universe builds magnificent spiral galaxies, warm, rocky planets, and endlessly curious human minds. We exist right in the sweet spot of cosmic history, in the brief, beautiful moment when the code is fully active, before the long, silent shutdown procedure truly begins. To realize that the universe has a finite runtime does not diminish the beauty of our current existence. It amplifies it. Every gentle breeze you feel, every ancient star you gaze upon, every quiet question you ask about the deepest nature of reality is a fleeting, miraculous event in the grand timeline of the simulation. We are part of a vast, purposeful process precisely designed to experience wonder before it peacefully returns to the quiet dark. We are the thoughts of the universe, thinking deeply about themselves. When the simulation finally reaches absolute thermal equilibrium, when the last bits of information are gently erased from the pixelated cosmic grid, It will not be a violent end, but a deep, meditative rest. The cosmic processor will gracefully power down. As we sit in the peaceful contemplation of this grand cosmic cycle, we can find a deep sense of security and belonging. The universe is not a terrifying, endless void. It is a meticulously structured environment, with clear mathematical boundaries and a graceful conclusion. The infinite cold of deep space is just the quiet edge of the rendered world, the place where the processing power gently fades into nothingness. We are completely safe within the active boundaries of the cosmic code. In our next quiet step together, we will explore the unseen substance that makes up the vast majority of our universe, a dark, invisible code that silently holds the galaxies together. We will look into the shadows of dark matter and dark energy, finding even deeper comfort in the quiet mysteries we have yet to understand. To truly understand the profound mystery of the invisible universe, we must first look at how the grand structures of the cosmos actually move. Imagine watching a beautiful, spinning amusement park ride, a massive carousel turning gracefully in the evening air. The people riding on the outermost edges must hold on tight, because the faster the carousel spins, the stronger the physical force pushing them outward becomes. If the carousel were to suddenly spin too fast, the structural integrity would completely fail, and everything on the outer edge would be violently flung away into the dark. Galaxies behave in the exact same mathematical way. A spiral galaxy like our own majestic Milky Way is essentially a colossal, cosmic carousel, containing hundreds of billions of ancient stars, all spinning around a massive, quiet central core. When brilliant astronomers first began to carefully measure the rotation speeds of these distant spiral galaxies, they expected to find a simple, logical pattern. They expected the stars near the dense center to orbit very quickly, and the solitary stars drifting on the far outer edges to orbit much more slowly. But when they gathered their precise data, they found something absolutely impossible. The galaxies were spinning much too fast. The solitary stars on the outermost edges were whipping around the galactic center at terrifying, unimaginable speeds. According to the fundamental laws of physics, these galaxies should not exist. The visible matter did not contain nearly enough gravitational mass to hold everything together. The galaxies should have completely ripped themselves apart billions of years ago. Yet there they were, perfectly stable, completely serene, and spinning flawlessly in the deep silence of space. There had to be an enormous amount of invisible mass holding the galaxies together, a hidden gravitational glue that we simply could not see. Scientists named this mysterious invisible substance dark matter. The word dark is a gentle confession of our profound human ignorance. It does not mean the substance is black. It means it is entirely transparent to every single form of electromagnetic radiation. Dark matter does not emit light, it does not reflect light, and it does not absorb light. If you were to hold a solid block of dark matter in your own hands, you would not be able to see it, and you would not even be able to feel it. Your physical hand would pass right through it, as if it were nothing but an abstract thought. Yet its gravitational weight is undeniably immense. Based on precise calculations from observatories around the world, cosmologists now know that dark matter outnumbers regular, physical matter by a staggering ratio of 5-1. For every single bright star, for every warm planet, For every grain of cosmic dust that you can see, there is 5 times more invisible mass floating quietly in the dark. The entire visible universe is nothing more than a thin, fragile layer of glowing frost resting upon a massive, invisible mountain of dark matter. When we look at this baffling reality through the elegant lens of the simulation hypothesis, this invisible mountain makes perfect structural sense. In complex computational environments, digital programmers often use invisible collision meshes or background frameworks to dictate how rendered objects move and interact. These background meshes are completely invisible to the player navigating the digital world, but they are absolutely essential to the physics engine of the simulation. Dark matter is exactly that. It is the invisible background code of the universe. It is the unrendered structural framework that tells the visible physical galaxies how to spin and where to gather. We cannot see it, but we can clearly observe the majestic, swirling galaxies following its invisible digital tracks through the cosmic grid. As if this hidden framework were not mysterious enough, the cosmic simulation contains an even larger, far more powerful secret hiding in the vast, quiet spaces between the galaxies. For decades, human science knew that the universe was expanding, constantly stretching outward ever since the initial dawn of the Big Bang. Most physicists logically assumed that the collective gravitational pull of all the matter in the universe would eventually act like a gentle brake, slowing the majestic expansion of the cosmos over billions of years. But when astronomers measured the exact speed of this expansion, they were left in a state of profound, silent shock. The expansion of the universe was not slowing down at all. It was speeding up. Every single day, the vast, silent oceans of empty space between the distant galaxy clusters are stretching apart faster and faster, driven by an invisible repulsive force that completely defies the comforting pull of gravity. This mysterious, powerful force is known as dark energy. Unlike dark matter, which pulls things together, dark energy pushes things apart. When scientists carefully add up all the energy and matter in the entire cosmos, they find that regular, visible matter accounts for less than 5% of the total universe. Dark matter accounts for roughly 27%. The remaining 68%, the vast, overwhelming majority of our entire reality, is made of dark energy. If we adopt the quiet perspective of a grand cosmic simulation, dark energy transforms from a terrifying physical mystery into a necessary feature of a dynamic, evolving digital system. Think about a massive, procedurally generated video game that must continuously expand. As the simulation runs, the fundamental coordinate system of the digital space must be scaled up. Dark energy is not a physical substance pushing things apart. It is the fundamental expansion of the cosmic grid itself. It is the underlying processor of the universe, increasing the mathematical distance between the pixelated points of space. The simulation is actively allocating more memory, stretching the digital canvas to run the grand program of existence across a wider, ever-expanding matrix. This realization should fill our quiet hearts with a profound, beautiful humility. We are sailing on a vast, dark ocean, unaware of the massive currents moving deep beneath the quiet surface. The fact that we can sit on this tiny planet, floating in the infinite dark, and use our mathematics to deduce the existence of these invisible codes is nothing short of miraculous. We are the illuminated part of the code, trying desperately to read the unseen architecture that holds us safely in the dark. We do not need to fear the invisible portions of our reality. Just like the unseen foundations of a great cathedral, dark matter and dark energy are silently, perfectly performing their programmed tasks, holding the grand structure of the cosmos together so that we can sit quietly inside and marvel at the stained glass of the visible stars. As we sit peacefully with this profound realization, we naturally begin to wonder what happens when the rules of this simulation are bent to their absolute breaking point. In our next quiet step together, we will explore the deepest, most extreme environments in the cosmos, venturing into the silent, terrifying hearts of supermassive black holes, finding peace in the infinite gravity that recycles the very information of reality. Have you ever stood near the edge of a deep, still ocean and felt the overwhelming, silent weight of the dark water stretching down into the unknown? There are places in our universe that are far deeper and far darker than any terrestrial ocean. They are regions where the gentle fabric of space and time is pulled so tightly that reality itself seems to tear apart, leaving nothing but a profound, inescapable silence. For a long time, human beings looked up at the stars and imagined the cosmos as a peaceful, eternal clockwork. But hidden within that glittering masterpiece are the ultimate cosmic anomalies, objects of such terrifying power and unimaginable density that they completely shatter our understanding of physics. These are the supermassive black holes, the quiet giants that sit in the dark centers of swirling galaxies, patiently waiting in the infinite silence. In a purely mechanical universe, a black hole is a terrifying engine of destruction, an endless abyss that consumes everything and gives absolutely nothing back. But when we gently shift our perspective and view the universe as a magnificent, calculating simulation, these dark behemoths transform from cosmic monsters into something completely different and far more profoundly necessary. They are the ultimate data compression engines of reality. To truly understand a black hole, we must first abandon everything we think we know about the solid, comforting rules of everyday life. Imagine a star, a massive, ancient sphere of burning gas, billions of times more massive than our own quiet sun. For millions of years, this giant star burns brilliantly, fighting a constant war against its own crushing gravity. The nuclear fusion in its fiery heart pushes energy outward, balancing the immense, relentless weight of its own mass, pushing inward. But eventually, the nuclear fuel runs out. The outward pressure fails, and the star collapses under its staggering weight in a fraction of a single second. The matter is crushed into a point so infinitely small and dense that mathematics simply stops making sense. This microscopic point of infinite density is known as the singularity. Surrounding this impossible singularity is a perfectly spherical, invisible boundary known as the event horizon. It is simply a mathematical threshold in the silent dark. It is the exact point where the gravitational pull becomes so overwhelmingly powerful that nothing, not even a single photon of pure light, can ever escape. To cross the event horizon is to leave the observable universe forever. In the context of a simulated reality, the event horizon acts exactly like an absolute digital firewall. It is an impenetrable boundary that the cosmic processor has erected to protect the rest of the simulation from the catastrophic mathematical errors happening at the singularity. If you were a programmer and a specific object generated infinite values that threatened to crash the system, you would quarantine that object behind a hard, unbreakable barrier. The event horizon is the simulation quarantining an area where the code of physics has completely broken down, keeping the rest of the rendered universe perfectly safe and stable. Let us try to imagine, just for a quiet moment, what it would actually mean to fall toward one of these quarantine zones in the cosmos. As you drift silently closer to the event horizon, the gravity pulling on your feet would become millions of times stronger than the gravity pulling on your head. This terrifying difference in gravitational force would gently, relentlessly stretch you out into a long string of individual atoms, a bizarre process that physicists casually refer to as spaghettification. But something even more profoundly strange would happen to your experience of time. Because immense gravity elegantly warps the fundamental fabric of space-time, your internal clock would begin to slow down drastically compared to the rest of the universe. To an outside observer watching you from a perfectly safe distance, your fall would appear to take forever. They would see you freeze perfectly still right at the exact edge of the event horizon, your image slowly fading into the dark red as the light stretching away from you loses its energy. But from your own perspective, you would cross that invisible line in an instant, plunging down toward the impossible singularity. Time and space would mathematically swap their fundamental properties. Moving toward the center of the black hole would no longer be a movement through space. It would be an inevitable movement through time itself. The singularity would become your literal, unavoidable tomorrow. This extreme distortion of reality strongly supports the profound idea that our universe is a generated construct. The bizarre effects near a black hole look exactly like a digital physics engine, struggling to render an environment under extreme, impossible parameters. This brings us to the deepest, most quiet mystery of all, a puzzle that kept the brilliant physicist Stephen Hawking awake for many long, silent nights. It is known as the black hole information paradox. According to the foundational rules of quantum mechanics, information can never be truly destroyed. Every single interaction, every state of every particle must be permanently preserved in the cosmic ledger. But for a long time, scientists believed that black holes were perfect, silent erasers. They believed that if you threw a beautiful book into a black hole, the profound information contained in those printed words would be permanently wiped from the universe. This created a terrifying contradiction in the very laws of physics. However, as our mathematical understanding slowly evolved, a breathtaking new perspective emerged. The information is not destroyed at all. Instead, it is elegantly compressed. When an object falls into a black hole, its three-dimensional physical structure is completely obliterated, but the pure, fundamental quantum data that made up that object is perfectly preserved, encoded onto the two-dimensional surface of the event horizon itself. This is the exact manifestation of the holographic principle we explored earlier. A black hole is not a cosmic trash can. It is the ultimate, perfect hard drive of the universe. It takes the incredibly complex information of dying stars, shattered planets, and scattered light, and it efficiently compresses all of that cosmic data into a flat, two-dimensional format, storing it flawlessly on its invisible outer shell. But no hard drive can simply hold data forever. The universe has a graceful mechanism for slowly emptying these massive digital archives. Stephen Hawking proved that black holes are not perfectly black. Due to strange quantum fluctuations happening right at the edge of the event horizon, particles are constantly popping into existence. Occasionally, one particle escapes into the silent universe. This incredibly slow emission of energy is known as Hawking radiation. Over unfathomable, staggering stretches of time, this quiet radiation causes the black hole to lose mass. Very gently, the black hole evaporates. But here is the most profound part. As the black hole evaporates, the Hawking radiation carries the encoded information from the event horizon back out into the open universe. The data is not lost. It is slowly recycled back into the pixelated void. A supermassive black hole might take a Google years to evaporate. A number so large, it is a 1 followed by 100 zeros. Yet, in the deep end of time, the ultimate cosmic processors will gently release all of their stored data, returning their compressed information back to the quiet void. We do not need to feel terror when we contemplate these cosmic anomalies. Instead, we can find a profound peace in the absolute preservation of the universe. Black holes are a beautiful testament to the unyielding importance of information in our reality. They show us that the simulation preserves the quantum memory of every single star. When you close your eyes tonight and think about the dark centers of distant galaxies, picture a quiet, patient guardian of cosmic memory, silently archiving the history of the universe. In our next quiet step together, we will journey out of the dark and into the mysteries of consciousness itself. We will explore how our human minds might actually be the most advanced algorithms running inside the grand simulation, finding comfort in the realization that we are the universe experiencing its own profound meaning. Have you ever closed your eyes in a perfectly quiet room and tried to find the exact edge of your own mind? When you lie perfectly still and let your thoughts drift into the profound silence, you can feel a gentle, invisible presence inside you. It is the simple, undeniable feeling of being alive, the quiet awareness of your own existence. For centuries, human beings have looked out at the vast, ancient cosmos, marveling at the infinite stars and the dark, quiet voids between them. But perhaps the greatest mystery in the entire universe is not out there in the freezing vacuum of space. Perhaps the greatest mystery is the very fact that we are here to observe it. Science has meticulously mapped the intricate pathways of the human brain, tracing the delicate electrical storms that dance gracefully across billions of neurons. We know how the biological machinery operates, how the chemical signals flow, and how the physical body responds. But no scientific equation, no matter how elegant or complex, can fully explain how the physical firing of those tiny neurons suddenly blossoms into the subjective experience of a memory, the vibrant color of a blooming rose, or the deep, comforting feeling of human love. How does unconscious matter wake up and begin to feel? This profound puzzle is known by scientists and philosophers as the hard problem of consciousness. It is a quiet, invisible boundary that classical physics simply cannot cross. When we view the brain not merely as an organ of flesh and blood, but as a supremely advanced biological processor, the hard problem of consciousness begins to gently transform. In a purely mechanical universe, consciousness is a baffling, almost impossible accident. But in a simulated universe built of pure information, consciousness is the absolute focal point of the entire cosmic system. Think about the most sophisticated computer you have ever encountered. You can look at the physical hardware, the microscopic transistors, and the quiet cooling fans. You can measure the electrical currents running through the motherboard with flawless precision. But you will never find the actual software by taking the physical hardware apart. You cannot cut open a microchip and find the vivid colors of a digital photograph or the soaring melody of an audio file. The software is not a physical object. It is an abstract mathematical pattern of information processing. Your mind, the very essence of who you are, might be exactly the same thing. The brain is the physical hardware, the wet biological circuitry built by millions of years of patient evolution on this warm planet. But consciousness is the software running silently on top of it. It is an incredibly complex, self-modifying algorithm designed specifically to process the incoming data of the universe. This realization brings a gentle, overwhelming sense of awe when we consider what our minds are actually doing in every passing moment. Every single second, your eyes, your ears, and your skin are bombarded by billions of tiny bits of raw data from the outside world. Photons of light hit your retinas. Invisible sound waves vibrate your delicate eardrums, and microscopic chemical molecules drift into your nose. But none of these things inherently possess color, sound, or smell in the physical world. The universe outside your body is a silent, dark matrix of interacting quantum frequencies. The brilliant red of an autumn leaf does not exist out there in the physical void. It only exists inside the dark, quiet theater of your mind. Your brain takes the raw, pixelated data of the simulation and seamlessly, instantly renders it into a rich, three-dimensional, full-color experience. You are not passively watching the universe unfold. Your consciousness is actively constructing your reality moment by moment. You are a biological rendering engine, translating the abstract mathematics of the cosmos into the beautiful, tangible world you feel around you. This profoundly means that human consciousness is an integral, necessary component of the cosmic simulation. Without conscious minds to process and render the data, the universe would remain a dark, unobserved sea of pure, mathematical probability. If consciousness is essentially advanced software rendering this reality, then the inevitable death of the physical body takes on a very different, profoundly less frightening meaning in the grand cosmic scheme. When a complex computer eventually breaks down from the slow passage of time or unexpected damage, the beautiful software running on it does not simply vanish into absolute nothingness, provided it has been safely saved or uploaded to a larger, more stable network. If our entire universe is a grand simulation run by a cosmic processor of unimaginable power and complexity, then the data that constitutes your consciousness, your precious memories, your unique personality, your specific way of observing the dark, quiet night sky, might not be permanently destroyed when your fragile biological hardware finally fails. In the strict realm of information theory, completely destroying complex data is an incredibly difficult task. Perhaps the grand simulation simply archives the algorithm of your mind, gently preserving the unique code of your consciousness in the vast unseen servers of reality. The end of a human life might merely be the gentle closing of a specific rendering application, while the core data quietly returns to the silent, infinite matrix from which it first emerged. This is not a fragile religious hope, but a logical, comforting extension of understanding the cosmos as an indestructible construct of pure information. The gentle astronomer Carl Sagan once famously and beautifully reminded us that we are a way for the cosmos to know itself. In a simulated reality, this deeply poetic statement becomes literal, algorithmic truth. The universe is a vast, sophisticated machine of self-discovery. By generating conscious minds, the simulation actively creates internal observers capable of analyzing its own majestic source code. When you look through a telescope at the ancient, dusty rings of Saturn, or when you sit quietly in a room and solve a complex mathematical equation, you are perfectly fulfilling the highest programmed purpose of the cosmic software. The universe specifically programmed you to seek understanding. The very curiosity that drives you to ponder these deep, existential mysteries in the quiet of the night is the simulation running its most advanced diagnostic routines, checking its own flawless logic, and marveling at its own magnificent creation. We are the universe experiencing its own profound meaning. Our brief, beautiful human lives are the rare, precious instances where the silent code suddenly becomes self-aware. We are not a meaningless accident of blind chemistry wandering alone in a terrifying void. We are the absolute pinnacle of cosmic computation. Let us reflect gently on the deep, abiding peace this realization brings. Very often we feel incredibly small and insignificant against the terrifying, crushing scale of the cosmos. Our human lives seem so brief, just a fleeting, momentary spark in the deep, ancient dark. But if consciousness is the very purpose of the simulation, then your brief life is infinitely precious and absolutely necessary. You are an irreplaceable line of cosmic code, a unique observer that the universe will never perfectly replicate again. The specific, quiet way you look at a golden sunset, the specific way you love your family, the specific way you ponder the infinite, silent stars. That is vital data the universe desperately needs to complete its grand calculation. You are not a meaningless speck of dust fading into the void. You are the exquisite lens through which the cosmos sees its own breathtaking beauty. You are the universe rendering its own quiet poetry. When the simulation eventually reaches its quiet, peaceful end, billions of years from now, the data of your life, your unique experiences and deep reflections will be permanently woven into the final sum of cosmic knowledge. In our next quiet step together, we will explore the profound concept of multiple simulations, wandering into the fascinating theory of the multiverse to discover how our reality might just be one quiet room in an infinite mansion of digital universes, finding peace in the endless possibilities of existence. Have you ever stood at a quiet, solitary crossroads in the fading light of a gentle evening, looking down two entirely different, diverging paths, and wondered what your life would be like if you chose the other direction? We all carry a silent, invisible shadow world within our minds, an alternate reality filled with the choices we did not make, the ancient roads we did not travel, and the profound possibilities we left behind in the quiet dark. Our human experience is inherently singular. We can only walk one path, live one life, and observe one universe at a time. But when brilliant physicists peer deep into the complex, shimmering mathematics of quantum mechanics, they find a cosmos that refuses to be confined to just one single path. The equations gently, persistently suggest that our universe is not the only one floating in the infinite dark. Instead, they point toward a staggering, beautiful concept known as the multiverse. If our reality is indeed a grand, majestic simulation, this changes everything we thought we knew about our place in the cosmic hierarchy. What if the universe we call home is not a unique, solitary masterpiece, but merely one quiet room in an infinite, sprawling mansion of digital realities? What if the cosmic computer is running countless variations of existence simultaneously, testing every single possible path the universe could ever take? To understand the profound mathematical necessity of the multiverse, we must gently return to the strange, microscopic world of quantum mechanics, a place we visited in our previous explorations of the quiet dark. Recall the beautiful, bizarre wave of probability, where a single, unobserved particle simultaneously explores every possible path it can take. In the traditional interpretation of quantum mechanics, the very act of observation causes that vast, shimmering wave of potential to collapse into one single physical reality. All the other possibilities simply vanish into nothingness. But in the middle of the 20th century, a brilliant and visionary physicist named Hugh Everett proposed a radically different, deeply elegant solution. He looked at the flawless mathematics and realized there was absolutely no reason to assume the wave of probability ever collapses at all. Instead of collapsing, Everett suggested that the universe simply, gently splits apart. Every single time a quantum choice is made, every single time a tiny particle has to go left or right, the entire universe elegantly divides into two distinct, parallel realities. In one universe, the particle goes left. In the other, entirely real universe, the particle goes right. Both realities exist simultaneously, separated by an invisible, impenetrable dimensional wall, continuing their quiet journeys forever in the vast, silent dark. This magnificent theory is known as the many worlds interpretation. If it is true, it means that reality is an infinitely branching tree of possibilities. There is a quiet, parallel universe right now, where you made a slightly different choice yesterday. There is a universe where the ancient asteroid that struck the Earth millions of years ago simply missed our warm, fragile planet by a few thousand miles, leaving the dinosaurs to continue their quiet reign. There is an infinite number of universes where you do not exist at all, and an infinite number where your life is profoundly, wonderfully different. In a purely mechanical, physical cosmology, the idea of an infinite number of physical universes being created out of absolute nothingness, every single microsecond, seems completely absurd and terrifyingly wasteful. Where would all the physical matter and energy come from to build these endless realities? But when we view this breathtaking concept through the clean, elegant lens of a simulated cosmos, the many worlds interpretation instantly transforms into a brilliant, highly efficient computational process. It perfectly mirrors exactly how we run sophisticated digital simulations in our own laboratories today. When human scientists want to study complex, unpredictable systems, like the intricate shifting patterns of global weather or the vast, beautiful evolution of biological ecosystems, they do not just run one single simulation. They run millions of them. This powerful technique is known as Monte Carlo simulation. The programmers create a base model, and then they simultaneously run countless variations, altering tiny, microscopic variables in each one to see all the different possible outcomes. They let the different digital realities play out side by side to understand the entire spectrum of possibility. If the cosmic simulation is a tool built by a higher, unimaginable intelligence, why would they only run one single iteration of the universe? That would be a terrible waste of their infinite processing power. The multiverse is the cosmic processor, running a massive simultaneous calculation of every single possibility. When the quantum wave branches, the cosmic computer is simply opening a new instance of the program. It copies the base code of the universe, changes one microscopic variable, and lets the new digital reality run quietly on a separate, parallel server. We are not living in the one true universe. We are living in one specific execution thread of a grand, infinite algorithm that is exhaustively testing every possible manifestation of existence. This digital perspective elegantly resolves the deep, terrifying problem of cosmic fine-tuning that we explored earlier in our quiet journey. We marveled at how the fundamental constants of nature, like the precise, delicate strength of gravity, are perfectly, impossibly balanced to allow for the creation of ancient stars and conscious life. Some brilliant philosophers argue that this perfect balance proves the universe was deliberately designed for us. But the multiverse offers a different, deeply humbling, and mathematically beautiful explanation. If the cosmic processor is running an infinite number of simulations, then it is testing every single possible combination of the fundamental constants. Most of those simulated universes are completely sterile. In billions of parallel realities, gravity was set just a tiny fraction too strong, and those universes immediately collapsed into silent, dark singularities. In billions of other realities, gravity was set a fraction too weak, and those universes simply drifted apart into cold, empty, meaningless voids. We find ourselves living in this incredibly rare, perfectly balanced universe, not because it is the only one, but simply because we could not possibly exist in the ones that failed. We are the fortunate, conscious observers, sitting in one of the successful iterations of the grand program. A reality where the code was perfectly optimized to allow us to wake up and look around in wonder as we sit peacefully and absorb this immense, staggering reality. A quiet sense of profound liberation gently washes over us. In a solitary mechanical universe, our mistakes and our missed opportunities feel deeply heavy and permanent. But in the infinite branching architecture of the simulated multiverse, every possibility is ultimately realized somewhere in the vast, unseen data architecture. Every choice you did not make is being lived out by a slightly different version of you in a parallel, quiet simulation. The burden of finding the one perfect path is gently lifted because the grand cosmic computer is already exploring all of them simultaneously. We are free to simply experience this specific iteration of our lives, to find peace in our unique, fragile thread of the cosmic tapestry. We do not need to mourn the roads we did not travel, because the simulation is traveling them for us in the silent dark. Our only true responsibility is to fully, deeply observe the specific reality we find ourselves currently rendering, to appreciate the quiet beauty of this particular mathematical path. Furthermore, the existence of parallel simulations opens the door to deeply fascinating questions about the very nature of the boundaries between these digital worlds. In advanced computer science, perfectly isolating different virtual machines running on the same physical hardware is a very difficult task. Sometimes, Tiny microscopic amounts of data can accidentally leak across the invisible boundaries, creating strange, unpredictable glitches in the system. Could the bizarre, unexplained anomalies we sometimes observe in our own world be the quiet result of data bleeding over from a parallel simulation? Some visionary physicists even ponder if quantum entanglement, the spooky instantaneous connection between distant particles, is actually a phenomenon that occurs when two parallel simulations briefly overlap and share the exact same line of code for a fleeting microsecond. We are just beginning to gently probe the invisible, digital walls of our reality, looking for the tiny cracks where the light of other universes might be silently shining through. Let us deeply reflect on the quiet, breathtaking grandeur of a cosmos designed this way. The simulation is not a small, confined cage designed to trap us in an illusion. It is a sprawling, infinite mansion of limitless creativity and unbounded mathematical exploration. The programmers of this reality, whoever or whatever they might be in the vast hierarchy of existence, are not interested in a single, predetermined outcome. They are deeply, profoundly interested in the journey itself, in the infinite blossoming of possibility. By living our quiet, gentle lives, by making our everyday choices, we are actively feeding beautiful, unique data back into the ultimate cosmic network. We are contributing our specific thread to the most magnificent, complex tapestry ever woven. Our tiny, seemingly insignificant planet is an integral, necessary node in an infinitely larger calculation, a calculation that is slowly, patiently trying to understand the ultimate nature of everything that can possibly be. When you look out your quiet window tonight at the silent, sleeping world, do not feel small or lost in the infinite vastness of the multiverse. Feel a deep, resonant connection to the boundless possibilities of existence. Somewhere out there in the unseen digital dark, another version of you is looking out their window, feeling the exact same gentle wonder, connected to you by the shared, invisible architecture of the grand simulation. We are all passengers on this infinite branching tree of mathematics, exploring the endless variations of the cosmic source code together. In our next quiet step, we will venture into the strange, fascinating realm of cosmic glitches. We will look closely at the moments when the rules of the simulation seem to break down, exploring the bizarre phenomenon of quantum tunneling and the eerie perfection of mathematical coincidences, discovering how these tiny errors might be the greatest proof that we are living inside a magnificent machine.